So this one is about magic numbers and atomic structure, and it would appear that in order to maintain stability in a nucleus, multiples of 2 are required, just as with electrons. This is because one acts as the counterweight to the other, and in a binary orbit, they hold each other in place. Without an opposite, the proton or neutrons slowly work their way out of orbit, and the gravitational pull, when they do this, they tend to attract towards other neutrons and protons and eventually collide into the smallest possible balance state, helium, only 2 needed. This is why we have alpha decay, as once this happens, they have enough energy to be unbounded from the nucleus. When all are paired up, they hold each other in orbit and maintain the atomic structure. Okay, so basically what I'm saying here is that it would appear that every molecule or every atom, right, is made up of kind of like a pairing structure. You know, you look at all the magic numbers and they're all even numbers. And, you know, we look at electron pairs and, you know, it's all pairs. It's even numbers, right? And so I think that the reasoning for that is that they're kind of like a balancing like weight to each other, right? If one is swinging over here, the other one kind of is reducing its energy to keep it in orbit. I got like a bug just staring at me, and it's kind of freaking me out. I don't like it. It's just like hovering there. I don't like it. Go away. You're freaking me out. It straight up just left. Oh, it's back. Anyway. So, it's just hovering so menacingly. I don't know why. It's weird. Things are so weird in this world. Like, what's going on? You know? Anyway. I'm talking about pairing for like magic numbers. And I think I don't really know. I can't explain atomic structure yet. I don't really know how exactly that all works. But my theory on why we have alpha decay and we don't tend to see anything larger than helium being like a decay process is that, you know, these, like, in a nucleus, you know, we've got these particles, you know, we've got the protons and the neutrons kind of orbiting around, kind of keeping each other in balance or whatever, but it's not a perfect balance, right? It's not always a perfect balance. Because if there's just a slight little inconsistency or, you know, the energy is slightly disrupted, what happens is that these orbits get kind of unaligned, right? And so they're orbiting each other, and then, you know, eventually they will kind of, you know, be orbiting, and some of these might get closer than, you know, they normally would, right? And so as they get closer and closer together, right, now you have a proton and a neutron, and, you know, that increases the mass that's, you know, there. And now these two things are orbiting together, right? But they're not strong enough to break out of the entire orbit, like the gravity of the nucleus itself, right? So their gravity is increased between them, but the gravity of these two particles together is not enough to break out of the overall nucleus, right? So they're still stuck in that gravity well. But as you pull in, another proton gets attracted to it because it is a larger mass. So inside of this gravity well, there's another gravity well. This gravity well slowly pulls in, another proton, and then it pulls in another neutron. And at this point, they're heavy enough to escape. And a big reason, I talk about this with electrons, a big reason why a lot of electrons can't escape their orbitals, right, is because as they start to get out, they don't have enough energy. They build up energy, but they don't have enough energy to continue them, continue defying the gravity of the nucleus. They don't have enough energy to defy the gravity of the nucleus. And so at a certain distance, the gravity of the nucleus pulls on them stronger than outside particles. But if you give that electron enough energy, then it can achieve escape velocity and break out. And if there is another atom nearby that gets close enough, it can jump ship, right, and move over to that nucleus instead, because it gets pulled over there once it's far enough away. The strength of the other one pulls it in, right? And so that's what's going on with electrons. But electrons don't have their own effective energy production system, right? They're not spitting out energy, right? They're not producers. And the mechanics of this production process are not perfectly known, but basically, you look at a black hole and it sends out Hawking radiation. I think this Hawking radiation is sort of what a proton is sending out. And electrons probably have some kind of radiation going on, but it's not energetic enough to allow them to grow. Right? It takes more energy to maintain their structure than they have, right? So in order to maintain their structure, they got to burn energy. I would say that protons and neutrons decay into protons, so neutrons would be able to do this if they didn't have that little electron, inside there, kind of sucking everything up. And so, I don't know. I'm talking about this. I'm really kind of workshopping this on the fly because I'm not exactly certain on this structure, but I'm hoping that something can be gleaned from my rambling here, because basically, not once you have helium is stable because it's got that counterweight kind of thing going on, right? And so it all, not only does it have enough mass, but it also has, its own energy production method, and it's at a balanced state where basically, it doesn't need to worry about, do I have enough energy to escape, because it's basically unbound. It's almost as if it's in zero gravity, because once it has its own energy production method, it almost creates like a bubble of zero gravity around it. Is potentially what's happening there, right? It's creating almost like a bubble of zero gravity, and so the global gravity of the nucleus is no longer relevant. It doesn't matter anymore. And you may say, what? How? Right? Well, Well, let's think about this. We have maglev trains, right? These maglev trains are levitating trains, which are heavy, right, off the ground. How are they doing this? They're defying gravity with their magnetic field, right? And so basically you put like a little bubble on the ground, and so, you know, if you could continue that, you know, magnetic repulsion, you could just lift it up and just keep going up all the way to space, and, you know, that train would never touch, you know, your thing. It would just keep flying up in the air if you could do that, right? And so I think, you know, basically that's what's happening there, is that it creates its own field of I want to say, I think that magnets are basically the lack of energy, right? Magnets create a zone of low energy, and low energy means there's a smaller amount of vacuum energy or virtual particles in that area. And what I think could be happening here is that protons reach, like, I mean, helium is when like escape mass is achieved, almost, because pretty much it's flying around, right? It's flying around, so it has angular velocity, right? But once it reaches this escape mass, I'm just making this up, I don't know if this is really a good term for it, but I'm just kind of doing it. That bug's still buzzing around, by the way. You know, you have this escape mass, and so it's flying around, it has angular velocity, and boom, all of a sudden they finally coalesce, it all comes together, and now it has effectively, how I believe gravity works is that there's just particles, and so it gets pulled towards the direction of, you know, like the particle motion. And so with gravity, you know, you have particles that are not moving over here, right? And then you have particles that are not moving over here, and you have particles that are not moving over here. But the particles that are towards the large gravity, so the nucleus is over here, all of the particles, all of the vacuum energy, right, all the virtual particles are flowing, or getting pulled towards the nucleus, right? And because they're all getting pulled towards the nucleus, things that are out here in this space, you know, they're getting pulled towards everything equally, but the stuff over here is getting pulled this way, and so naturally they also get pulled in, right? As they're just kind of floating through these virtual particles, the only particles with motion are in any direction are the ones over here, and so it keeps its angular velocity, right? It's moving this way, so it's naturally getting pulled towards that with more favoritism, but it's also got a net pull, or net flow going towards the center of the nucleus, right? And so effectively, what I think happens when it finally reaches this stable, you know, escape mass is that the helium atom has pretty much made its own sea of particles that it's sending out, right? And now, instead of having a collective flow moving this way, there is effectively a collective flow coming out, and so there's just like a static, like, instead of there being a collective flow this way, there is just you know, a static flow out from the particle. And so since all of the particles are coming out of the helium atom, they all have, you know, basically the same level of pull, except the particles that are getting shot out in the direction of velocity of the angular velocity at the point it reaches this, right? Those are the ones that are going to be closest to it because it's sending those out, right? And we see this with like sound waves and stuff. It's called like the Doppler shift, right? So the particles in the direction of travel are going to be naturally the ones that get pulled on the most because they will be the closest because that is the direction it's moving. It's moving in that direction. It's sending these ones back. These ones are going to be farther and farther away. The ones in front of it are going to be closer and closer, right? As it's moving in that direction. So it maintains its velocity and just kind of whatever that coalition happens, it's now in its own bubble of self perpetuating gravity and velocity, and so it just continues on in that direction, and it doesn't really lose its velocity too much because it's sending out infinite particles because like I said, it's like a production and it's stable, so it's not losing energy over time because its mass and production rate. Again, this is getting it gets deep, and I don't have all the answers, and I don't know if I really care to go this deep because I don't want to be the person that solves everything. I'm just trying to point us in a direction here. All right, so these are my thoughts, and I might just leave it at this because I've got other things I got to do, right? There's other things I need to focus on, and this has been taking up too much of my headspace for too long. And so it reaches this point, and so I'm pretty sure nothing above helium is sent out as a particle. And the reason why is because as soon as helium forms, it's not bound anymore, and it can escape. And so that's why we have alpha decay. Because as soon as it reaches the first stage of, as soon as it reaches that escape mass, it flies off and it's gone, right? And we have this decay happen. But really what happens is that this helium particle has escaped the velocity of this quote-unquote other molecule. And protons are not able to do this because their mass is not at a high enough level, right? They're not sending, basically, I don't think they're capable of sending out enough particles to counteract the overall flow, right, of like the overall pull, the collective pull of the nucleus. The proton cannot send out enough particles to create its own self-perpetuating field that counteracts the global flow. But helium is that critical point, right? And it may be that it's not necessarily that critical point, but it's the only thing that's sustainable. So everything else, it may have enough mass to escape, but it doesn't have enough energy to escape because there's not enough energy being maintained in this system. And getting into how, protons send off this excess energy and why protons send off this excess energy compared to electrons and neutrons is potentially for the next person to figure out. I would say that it would probably have to do with the mass of a proton being a certain size, and it would also have to do with just the nature of infinity and how if energy is constantly bubbling up, it needs to bubble out into something, right? So you have this point of infinite density, right? And so we imagine, looking at the long-term scale of our universe, right? We say there's going to be heat death. The heat death the only way we can have the heat death is it's not going to be, everything's going to be space and then there's going to be black holes here and there. That at some point that will be the case where there's only black holes everywhere. But those black holes still have gravity and will have to all combine into basically one mega black hole. And when the entire universe is one black hole, that is when we have achieved heat death. But who's to say that if our entire universe is one black hole now, if our entire universe is one black hole, who's to say there's not a universe over there, and over there, and over there, and now they're all black holes? Well, now we have all these black holes again. They all got to turn into one massive black hole, right? And then it's like, who's to say there's not a black hole over there that's made up of a bunch of universes, and over there that's made up of a bunch of universes? Now they all have to coalesce, right? Right? And so we have this consolidation of bigger and bigger and bigger black holes, right? But if you really think about it, what is happening there? They are bubbling up into the next universe, right? So black holes could be the virtual particles of another universe, and they're collecting together, and then they collect into mass, right? And over time, all of these virtual particles collect into the mass, and then they get large enough that they basically create, like, this energy is coming from nowhere, but there's infinite nowhere for it to come from, right? So there is no such thing as empty space, and there is no such thing as nothing, and there is no such thing as zero energy, because infinity is so insane. And I think it makes the most sense. There is no atom. There is no fundamental particle. Everything is made up of nothing. But because there's infinite nothing for it to come from, we have infinite something to be made. And it's so crazy, but I love it. I love it. I think it makes so much sense. Everything is like, it's so crazy. Infinity is insane, and I love it. And I think that basically, I don't know. Basically, there is a lot of infinity that we can get energy from, and everything exists because. Why not? You only have to have a virtual particle come into existence, right? And annihilate and bump into another virtual particle, right? So now these two virtual particles are twice as much, right? And then it collapses back into this virtual particle, and now this virtual particle has excess energy, right? Because it was 2 minus 1, right? And now this one is, now it's still 1. But the collapse, when it collapsed, something was left over. And you only need that to happen once, for an instant. For an instant. It doesn't need to last forever. It only needs to overlap for an instant for there to be infinite energy for infinite time. And so, we say, what are the odds that we exist here? It's 100%. It's actually 100%. Well, it's obviously 100% because we're here, right? But at the same time, it is a guaranteed thing to happen because everything is relative. Everything is relative, right? So the amount of energy and the amount of time doesn't actually matter. It could be 0.00000000000000001 joules of energy, right? That's all that was ever made in the universe. But here's the thing. In a universe where there is nothing, absolutely nothing anywhere, that fraction of a joule is infinite energy, because as we know with entropy is that if there's high and low energy, it expands out, right? It expands out, and it needs to fill all of the free space. It needs to fill all of that space, and dissipate evenly. And we want an even distribution everywhere. And I mean, space is relative too, right? So like this could everything is relative. Everything is infinity, and it works. It works. You don't need a fundamental starting point. You don't need a fundamental, building block that everything works off of. In fact, a fundamental building block doesn't even really make sense when you really think about it. When you really think about it, for anything to be a thing, it needs to be made of something, right? And the only way that works is if you have infinite things to make up infinite things. And so, infinity is an inevitability. And we don't like it because it's like, oh no, infinities are scary. I think infinity is reality. And as much as we may not want to believe that, I don't think you're going to have much of a choice. So, yeah. And I don't even... What was I even talking about? I get way too into this. I barely even... I guess I covered everything I wanted to say, and then I got way deeper. This is why I'm trying not to do too many more of these talks, because I go on rants. No one's going to listen to this, like, almost 30-minute video. So, yeah. Anyway, peace out.